originally, thank you for the invitation. So originally I was going to focus more on isotropics and Weinstein domains, but I think it makes sense to actually begin the talk by saying a little bit about wrinkled embeddings, which Kai mentioned a little bit. And so I'll spend just a few minutes on this because this will play a role in the H principle for loose Lagrangians, which I'll get to. And hopefully by the end of the talk, I'll say a little bit about Weinstein domains, which are symplectic manifolds, which are built using Lagrangians and isotropics. Okay, so let me just give a quick sketch of wrinkled embeddings. And here, a wrinkle is a bit different from the wrinkle in Kai's talk. It's going to be a topological embedding from Rn into Rn plus one. Remember, Kai was talking about wrinkled submersions, and it's going to be smooth. It's going to be smooth embedding, except along an n-1 dimensional sphere in here, where there are cusps. I'll draw a picture in a second, and there are these unfurled swallowtails along the equator, which is a n-2 dimensional sphere living in here. So this is the equator here. Okay, so what do the pictures look like of these wrinkles? So for n equals 1, so this is the image of the wrinkled embedding in R2, and it has these cusps along 2 points, which is a zero-dimensional sphere. And there's no unfurled swallowtails. The n equals 2 case, it looks like you take one of these and you let them die in both directions. So you kind of take this, and then you let it die this way, and then you also let it die this way. So this is just half of the wrinkle. The whole wrinkle looks like it's a bit hard to draw. But basically, like you take a shirt and you kind of fold it over. This is what it looks like. So this is just half of this picture. And so in this case, there's an S worth singularities over here, and then at the 2 equator points, which is S0, you have the unfurled swallowtail. So that's kind of this singularity right here. Okay, so these are the wrinkled embeddings in this talk, and what's the relationship to the wrinkled embeddings in Kai's talk? So Kai's wrinkles. So these were submersions, but he talked a lot about the equidimensional case. So these are maps from Rn to Rn, and these submersions are projections of an inclusion of Rn into Rn plus 1. So when I say projection, I mean this projection. So the n equals 1 case, you take this curve, so that's a one-dimensional curve living in R2, and then you project it down to R1. So if you project down this way, so you take the line, you make a curve in R2, then you project it down to R1, and that's mapped from R1 to R1, and that's what Kai's wrinkled embedding is. And the n equals 2 case,
not embedding. Okay.
Sorry. Yeah. It's a submersion. The n equals 2 case, you take one of these curves looking at R2 and you let it die in both directions. So now it's gonna look like this. And this is again half of the n equals 2 case. And then again, you project down and you get an equal dimensional wrinkled submersion. Okay, so how are these two related? Well, to go from here to here, you make these vertical tangencies be sharp, and now they are no longer horizontal. That's the main idea. Right. Again, here you have these vertical tangencies, and here you have these sharp edges, and they're horizontal. They're not vertically tangent. So that's the main difference. Okay, and I'll explain why this is relevant in a second. So, okay, so these are wrinkles, and now I'm going to state the H principle for these. And for the H principle, you also need these embryonic wrinkles, which occur in one-parametric families, and these occur when a wrinkle is being formed. Like if you're starting from just a line, then there's a point like this embryonic wrinkle that occurs when you go from this straight line to this. Okay, so what is the H principle for wrinkled embeddings? So this is the theorem of Lazarev and Mishev. So I'm going to state, I guess I'll state the one parametric version, but well, let me state the zero parametric, the existence. So let's consider an embedding, a codimension 1 embedding, and a deformation of the tangent plane of this embedding. So it's let G of S be a map from this source into the Grassmannian, the n-dimensional Grassmannian of the target. So basically we're starting here, and if we're starting with so we have this deformation. This is covering F, and so that at time 0, this tangential deformation is actually equal to D of F. So basically, we're starting here at the tangent space of the embedding, and then we're doing this tangential deformation. So we're just rotating, and then the claim is then there is family of wrinkled embeddings. So these are these topological embeddings that have wrinkles. These are called, I guess, F of S. So that F of S is C0 close to F, and the derivative of F of S is C0 close to G of S. So you have this tangential deformation, and you can follow it through by a family of wrinkled embeddings. I should say, So this capital F of S, that's a wrinkled embedding, and I'm taking its derivative. And why does that make sense? Well, it's because I can talk about the tangent planes for a wrinkled embedding, even though it's just a topological embedding.
I should maybe say that when you what you call derivative is not the derivative as a map.
Yeah.
You just take the image of it.
Yeah. Sorry. So this should not be the derivative. This should just be the image of the tangent plane. Yeah. Any more questions? Yeah.
So sorry. So the GS we can see as an isotropy between the differential of f of little f and other mapping, or
Sorry. Say it again.
yeah, if GS
D.
like a deformation of the different.
What is D? What is DS?
G?
Oh, GS. Yeah. It's this. Okay. So you're starting with planes that are tangent to the image, and then you're deforming, and this family of deformations that is the GS. Yeah, and the claim is that this can be followed through by a family of actual wrinkled embeddings. So here you'll do these wrinkles, and here you'll do some more wrinkles.
Just to emphasize Kai's point, GS is not a family of maps, it's just a family of planes.
Yeah.
So why can't it be an embedding?
It is it's a topological embedding. It's just not a smooth embedding. And this is like if we had used Kai's wrinkles, then the tangent planes, like this is actually a smooth embedding, right? But the tangent planes here are vertical versus the tangent planes that we want to approximate are horizontal. So we have to add these sharp edges here. Does that answer the question? Okay.
Maybe a comment about also exactly this is that, I mean, what you're saying is you have a manifold, like an embedded thing, right? And now you have like some sort of formal movement of the first order data, right? And what you're asking is, can I holonomically approximate by an embedding? And in general, you cannot. I mean, we've seen several times that holonomic approximation is impossible, but you're putting some singularities that allow you to follow, to achieve holonomic approximation, and these are these wrinkles, right? And it's exactly what Oleg said, that this, well, this being flat is what's helping you.
One question. Sorry. So on the singularities, we take the limit. Is the limit of this C0 close to G?
Okay, so at the singularities, you can still make sense of this tangent plane, the image.
By taking limits.
Yeah, by taking limits. Yeah. And that's really what you're comparing here. Okay. All right, so that's the wrinkled embedding theorem. And now I'm gonna do a bit of a review about isotropics and contact structures, and then we're gonna use this wrinkled embedding theorem in that setting. Whoa. All right. So let me just get back into isotropics. Okay. Then we just begin with these fairly abstract definitions. Contact structure. The non-dimensional manifold is going to be a hyperplane field given by the kernel of one form, and this is contact if f alpha wedge d alpha to the n is non-zero. So this is a maximally non-integrable hyperplane field. So that means it's twisting as much as possible. And definition submanifold and the contact manifold is isotropic if the submanifold is the tangent planes of the submanifold are in this contact distribution. And there's a linear algebra lemma that says that if lambda is isotropic, then the dimension of lambda is at most n, where the dimension of the ambient contact structure, contact manifold, is 2n plus 1. And you should think of this as coming from the fact that these hyperplanes are maximally twisted. So they're twisted so much that you cannot have a very high dimensional manifold that's tangent to them. Okay. What are examples of this? So the main example of a contact manifold that we're going to be concerned with is the one jet space. The cotangent bundle across R. R will have coordinate Z, M will have coordinates Q, and the covectors will have coordinate P. And the standard contact structure is going to be the kernel of dz minus the sum of pi times dqi. And as Danny said, a section of the projection map is isotropic. So let's let the section be written as, so the P is going to be some function of the Q's, and the Z is also going to be some function of the Q's. If and only if the PI's are the partial derivatives of Z with respect to QI. So this is true if and only if the section S is polynomial. All right, because if you set this to 0, and you solve this, you'll get that, and you divide by dqi, you'll get that pi is the partial derivative of Z with respect to qi. Okay. So something that's isotropic is a generalization of holonomic section, but things don't have to be graphical. As Danny said, so in this whole talk, we're going to work in the front projection, and that's the projection for M cross R. And we can do that because for isotropic things, the P coordinates are recovered from the Z coordinates and the Q coordinates. So we can just work with the Q coordinates and the Z coordinates. The P coordinates up here can be recovered. So we're going to be working in this front projection. And here the pictures are exactly the pictures that we've been drawing in other talks. So here I have my Q variables, my Z variables. And I record the P variables by the slopes. So this is an example of a holonomic section, which gives me an isotropic submanifold of the one jet space, if I just take the P's to be the slopes. But there are also some non-graphical examples. So Danny talked about the case of a cusp. And this doesn't look smooth, but that's because we're working in the front projection. This actually is a smooth Legendrian in the one jet space. Another example, which is maybe a little bit easier to see that it's smooth. Well, you can have crossings, and this is not embedded in the front projection, but it is embedded in the one jet space. Well, because at this point, the two slopes are not the same. So the Q coordinates and the Z coordinates agree, but the P coordinates don't agree. And so in the one jet space, this is not actually an intersection point. You would have an intersection point if you have something like this, where the points agree and they're tangent, and this is what Arnold called the dangerous tangency, because it corresponds to an intersection point in the one jet space. Any questions?
Oh, could you say again in those two pictures, are they what are the variables on the axes?
This is Q, this is V.
Oh, same.
And I'm saying that like here, this is an embedding. Because at this point, the slopes are different. So the P coordinates are actually different, and hence in the one jet space, they correspond to different points. Versus this one is this is not an embedding. Because the Q coordinates agree at this point, the Z coordinates agree, and the P coordinates agree because the slopes are the same there.
So Q, Z in all pictures.
Say it again.
Q and Z are the axes in all pictures.
Yeah, in all the pictures. In the front projections, those are the variables, and we're going to only work with the front projection. Because again, for isotropics, the P variable can be uniquely recovered. Just by looking at the slopes. Okay. All right, well, these isotropics play a pretty crucial role in symplectic geometry. As I'll hopefully say by the end of this talk, you can actually build symplectic manifolds using isotropics. So classifying and understanding isotropics is arguably the main problem in symplectic geometry. Well, so how do we go about trying to understand these things and classify these things? Maybe first could consider local invariance. But unfortunately, or maybe fortunately, there are no local invariants. So let me just state that as a theorem. There's no local invariance. This is the Weinstein neighborhood. Neighborhood theorem, which says that I should say before I move on that okay, let me just make a remark over here. If we have an isotropic in a contact manifold, as Danny said, if k is equal to n, lambda is called a Legendrian, and if it's k is less than n, we're going to say lambda is subcritical. And usually when I say isotropic, I'm going to mean a subcritical isotropic, and the word Legendrian is going to mean a isotropic of an excellent dimension. So for this Weinstein neighborhood theorem, I'm just going to only focus on Legendrians, but there's going to be a version for isotropics which I won't state. So you have a Legendrian, then there's a neighborhood U of lambda in here, so that U with this contact structure on Y is contactomorphic to the one jet space of lambda with this like standard contact form that I discussed before, and this contactomorphism takes lambda to lambda. So if you have a Legendrian, it locally looks like just the zero section of the one jet space. Okay,
Is it J1 or a neighborhood of this of lambda in J?
I think you can actually make it just be the whole thing. That's it. Okay, well, to be safe, we could take a neighborhood. Okay. Type marker to. Let's say it's a neighborhood of lambda. But I thought you could take the one jet space, but you could definitely take the neighborhood. Okay. So there's no local invariance, which means that you have to have to study the global theory. Do you want to say anything about Legendrians? So now,
It's also a version for isotropics.
yeah, there's a version of isotropics. You have to remember the normal bundle. But for Legendrians, the normal bundle is determined by the Legendre basically. Yeah, I mean, in the one jet space, right, the normal bundle to the zero section is just given by the cotangent bundle of the Legendre across R canonical. And that's going to be true for any Legendre. But for subcritical isotropics, there's some extra potential data. So I was just choosing to avoid talking about that. Yeah.
There's a question about notation that maybe I didn't understand. N of lambda, it's referred to another a submanifold of the jet bundle, or
It's a neighborhood of the zero section
okay.
in the jet bundle. Okay. All right, so now let's move on to trying to state an H principle. So we need the formal data first. Formal isotropic or Legendre embedding. It's the same definition if you're subcritical or the maximal dimension is the data of f, little f, and big F of t, where little f is a smooth embedding. And big F of t is a family of monomorphisms covering little f so that at time zero it agrees with the derivative of f, which makes sense because little f is a smooth embedding, and at time one it's in the contact, it's in the contact structure. So you have a smooth embedding and you start rotating the tangent planes so that eventually each tangent plane is a Lagrangian plane in the contact distribution. Okay, that's the formal data.
It's just element in like a homotopy fiber from genre embeddings to embeddings.
I don't think so. Because both, like, neither of those words that you just used had anything to do with tangential homotopy.
It's more like the homotopy pullback of embeddings and isotropic inversion. respectful.
Also, sorry, Oleg, do you want F1 to be Lagrangian? The images of that?
Oh,
I think you need to.
yeah, okay, yeah, sorry. Okay, good, yeah,
Or isotropic, I guess.
yeah, or isotropic, yeah, sorry. Yeah, so you start rotating and you require that it is in the contact distribution, but that's not enough
It's a fullback.
to conclude that it's gonna be isotropic. You further require that it's an isotropic plane. Versus like if you actually are a smooth manifold and your tangent planes are in the contact distribution, then they are isotropic. But because we've decoupled the embedding from the tangential homotopy, we could pick whatever plane in the contact distribution that this could be, but so we have to additionally require that it's isotropic. Yeah, thank you, Danny. Okay. So
Sorry, can you repeat that last? I don't.
I'm just saying you have to have this condition that at time one, this tangent plane is isotropic.
But what is the extra condition versus what you already wrote?
I wrote that it just lies in the contact planes. But like this could have been like if you don't have this word, this condition is not like the formal data is more than just this being in the contact plane.
Maybe we should just remind people there's a formal symplectic structure.
Okay, yeah.
Contact distribution.
So a remark is that d alpha restricted to the contact distribution is a symplectic form.
Where locally the distribution is determined by alpha.
Yes. And so you could talk about isotropics in here, where this symplectic form vanishes. And yeah, okay. So maybe I see why this is a little bit confusing. Because my definition for isotropic was that the tangent planes of the submanifold lie in the contact form, like in the contact distribution, which actually implies that the tangent planes are isotropic in the sense that this two form vanishes on them, and that's for free actually when you're in the integrable case. But here we're not in the integrable case, we're just rotating the planes. And in principle, you could just start rotating the planes so that you end up at some plane in the contact distribution. And so you actually need this additional condition that the plane is an isotropic subspace with respect to this two form in the contact distribution.
So why is it like isotropic in the symplectic sense when it's integral?
I think that uses like a,
Because if alpha is 0, the alpha is 0.
right, yeah. For an integrable thing. Yeah. Right, so you do need this additional condition for the formal data. Okay. Any more questions? Maybe I can give something a bit else and provide some insights. Yeah. Okay, so let me state the first H principle, which is due to Gromov. That's full H principle holds for subcritical isotropics. So that's when the dimension of the isotropic is less than n. Isotropic embeddings. So you have genuine isotropic embeddings. And there's this forgetful map into formal isotropic embeddings, which I've just defined up there, and the claim is that this is a weak entropy equivalence if k is strictly less than n. And the proof idea is to, well, first you have to do a bit of work to reduce to the graphical case. So in the case where Y is a jet space and the Legendrian is a section, but it might not be a holonomic section, so it might be, so this is again Q and Z, it might be a section like this, where here I'm saying that the P coordinates are just given by the slopes of these. And then you have this additional homotopy that deforms these so that they're actually tangent planes. So I'm saying this is the actual embedding you're given. And then the formal data would be kind of like the rotation of these planes to like potentially planes that are tangent to this, but potentially some other isotropic planes. So there's some work to reduce the graphical case, and then you apply the holonomic approximation theorem. So this going up the mountain side, right? You want to go up the mountainside while having the same slope, and what you can do, because you have this extra dimension, is to go back and forth, and hence you can approximate this non-holonomic section by something that is holonomic. And again, the key point is for the holonomic approximation theorem, you need this extra dimension, and that's where this subcritical condition comes in. And note that here we don't use any wrinkles. So
Maybe only a comment that maybe it helps is that I mean, when we say graphical, right, it means that you're seeing your contact manifold locally as jet space of something. And I mean, the something is not the isotropic, because the isotropic is maybe, I mean, if k is smaller than n, the isotropic is too small to be the base of the jet space you look at. But you can thicken the isotropic a bit. So now it lives in like a neighborhood of a thickened thing. And okay, now you're in the jet space of that one. And now you do this. Yeah, what Oleg explained, right? You do holonomic.
yeah. Or if you want, this subcritical isotropic business is open Legendrians in H for the total.
Yeah.
Okay. So leave that there.
Does full H principle here include C0 dents?
Yes, and relative, yeah.
Okay.
So now let's move on to the Legendrian case. Legendrians.
Maybe one question, so the holonomic approximation theorem was for this, actually for some open manifolds, but here is there again, like, is there some hidden micro extension thing happening?
I thought there were two cases, right? One was for closed manifolds where the dimension was less.
Right.
And that used this micro extension.
But doesn't this micro extension only work in specific geometric?
Yeah, well, but I mean, that's exactly this thickening trick, right? Like an isotropic, you can thicken it to a Legendre. That is maybe the micro extension.
Okay, so for Legendrians, we would like to use embedding H principle, which is stated above. So what's the idea? And Danny already hinted at this. So we have a formal Legendre, right? This is not an actual Legendre because the p's are not given by the derivatives. And we would just like to approximate this by a wrinkled embedding, and the p's here are just given by the slopes, and these slopes are close to these slopes over here, and so this would be something at C0 close to the original non-Legendre. And the point is that, again, this looks singular, but it's only because we're working in the front projection. This actually is a smooth Legendrian because in the one jet space, this is smooth, and these cups appear only because we're working in the front projection.
Spiral.
Yeah, exactly. Yeah, in the one jet space, it kind of looks like a spiral. So theorem. This is due to Ilya Ashberg. Which is that, okay, so like this idea basically proves it in the one-dimensional case. That any smooth submanifold can be C0 approximated. Oh, sorry, any smooth n-dimensional submanifold can be C0 approximated by a Legendre. Okay, so again, the idea, this is the idea in the one-dimensional case. I'm going to say more about the higher dimensional case. But this is not, yes.
Is it easy to see that any smooth embedding is a formal Legendrian one?
No, but you don't need
I
that.
don't need that.
And this is not exactly, this is not the H principle yet. Right? Like I'm not saying anything about the formal class of this Legendrian, and I'm not requiring any formal data on top of this smooth manifold. Yeah. Okay.
Maybe a comment also about this is that when if you have a formal section of jet space, that can be turned into a formal Legendrian kind of quite canonically, so to say. So in this concrete graphical case, you can upgrade your sections to
It's just locally.
yeah.
Okay. Right. So again, this is not really an H principle because we're not requiring any. I mean, we're not requiring any formal data on the smooth Legendrian and arbitrary contact manifold, and also we're not saying anything about the formal class of this. So why am I emphasizing this? Well, it's because actually these zigzags that I've been drawing. So the issue is that in the one-dimensional case, this is not formally isotopic. Formally isotopic to not having the zigzag. And neither is the zigzag that goes back and forth. So actually when you add a bunch of zigzags, at least in the one-dimensional case, you're changing the formal class. And in fact, not every formal Legendrian rises as a genuine Legendrian. So meaning that if I have a formal Legendrian, it cannot be homotopic to formal Legendrian to genuine Legendrian for the case n equals 1. Because again, adding these zigzags, which is how one would try to build an actual Legendre changes the formal class. So just to make this a little bit more concrete, the proposition due to Murphy. Let's start with a codimension one submanifold of our Legendre. Then, so here's our U. We can add zigzags along U. I'm gonna add zigzags like this. You just take these zigzags and you kind of spin them around along U. So this is going to be formally Legendre isotopic to the one without zigzags, if and only if the Euler characteristic of U is 0. And so for n equals 1, the only codimension 1 submanifolds are just points, which have positive Euler characteristic. So adding these zigzags is always going to change the formal class. Whereas in high dimensions, you could take this to be a circle, for example, if n equals 2, and then adding these zigzags actually is formally isotopic to not adding the zigzags. So that's one difference between the low and the high dimensional case. Yeah.
Sorry, I missed the first explanation. U is the circle in this picture?
Use a circle in this picture. Yeah. But it could be any convention one. Okay. But that's just about the formal Legendre classes. But there's, I would say, a much harder theorem, the Etnar from Sullivan, that says that like adding wrinkles always changes the genuine isotopy class. So I have this stabilization, and this is never genuinely isotopic to the one without wrinkles. Then this is all relative boundary.
So this is like they are not on the right hand side? Or?
It's just like a patch of your Legendre. This is working well boundary. Yeah, if you want, you could close it up to be an unknot.
No, but I mean, if it was already loose, I guess, like
Right,
the right hand
it could have
side
been already
it doesn't matter.
Okay, yeah, the unknot. Oh no, I meant this rel boundary.
Oh, okay.
Rel boundary.
Okay.
Which is probably very close to doing it for the unknots. So you can't just start with a patch of your Legendre and just introduce zigzags where there were not any. So there, even though if the Euler characteristic is 0, you can formally do it, but you can't do it via a genuine Legendre isotopy. And so this actually requires some invariants that go beyond algebraic topology invariant. So here to prove this, you need some invariants like homomorphic curves. Something like local sheaves. Some flavor of symplectic invariance that goes beyond classical invariance like this bundle theoretic invariance. Okay.
Are those new invariants complete invariants? Or
I mean that's kind of a big open problem. Yeah, field. Okay. So to summarize. For n equals 1, we have this issue about the formal class. Wrinkles change the formal class. So it seems like it would be pretty hard to prove an H principle for the n equals 1 case. For n bigger than 1, wrinkles, you can arrange it so that the wrinkles don't change the formal class. But you need to assume existence of wrinkles. Start with, because this picture over here shows that you can't just form wrinkles where there were none. And so this seems to be kind of a not so great situation where you can't just form wrinkles for free. But as I'll turn out to say in a second, that there is an H principle if you assume the existence of just a single wrinkled piece. So, like in principle, you might think that there's no hope for an H principle because you could never form new wrinkles where there were none. And then maybe if you have one wrinkle, it's unclear how to get new wrinkles because this doesn't hold. But actually, just having like one wrinkle is enough to get many wrinkles. Yeah.
Is there any hope to prove that without the relative boundary? Say, assuming that it can be a global isotopy.
Yeah, if you don't do a real boundary, these are actually Legendre isotopic because you can you look at this picture, just kind of scale everything in, and I think you can like kind of move. Well, at least I don't know about a general U, but in the one-dimensional case, if you don't work real boundary, these are actually Legendre isotopic, right? You can just kind of shrink this in until you get to this patch.
I mean, that's homotopic, but not isotopic.
No, this is an isotopy. You have this piece of your Legendre, and you shrink it, and then you shrink it until you get just this line, and it's isotopic.
No, but I mean, that's a Legendrian homo.
No, but he's saying think of it with boundary and then just shrink the
Oh, I
boundary.
see.
But you can also do it globally for the loose ones that you're about to say
Ah, yeah.
in the closed case.
So what I was thinking is thinking of that as a local piece of whatever, close contact manifold.
Right.
Okay, so I'm going to state the H principle right now, and well, in maybe a minute, and then maybe they'll answer your question. Oh, so but anyway, this all shows that if you just work with Legendrians, this is not a weak homotopy equivalence for Legendrians. For n equals 1, it's not even surjective on pi 0. And well, this example shows that for a higher n, it's not injective on pi 0. Okay, so now let me define this single wrinkle that we're going to use to prove this H principle. So definition, a loose chart is a the Legendrian. I'll explain the rotation in a second. Maybe this is not the best notation. Okay, so here Z is this zigzag. Maybe it's more better to draw it like this, and in this cube with the standard contact form. And then you have to cross it by what is it? Okay, this is rho. Actually, maybe I can use some other verb. I'm gonna use S here. This is just the zero section inside of the piece of the cotangent bundle that's given by cotangent bundle of Rn, so that the q coordinates, their distance from the origin is less than s, and the p coordinates, their distance to the origin is also less than s. So you look at the piece of the cotangent bundle where the q coordinates are less than s, but also the momentum coordinates of distance less than s. So there's a bound on the slope, and it's loose if you require s to be bigger than 1, and I mean n should also be bigger than 1. So the picture is you have this zigzag, and then you cross it times kind of a thick enough.
Are you fixing the zigzag here, or can I pick my favorite zigzag?
You can pick your favorite zigzag, but there's some restraint on the slope.
Okay.
Because this is a cube, and so the p coordinate is measuring the slope, so the slope should be less than 1. Okay, maybe the slopes are negative, so maybe I should have drawn it like. But the slopes should be less than 1 because this is a cube. That's important. And so this with length is s. Okay, and so why is this size condition important? Well, for one, if there's no size condition, it turns out you can all like if you are okay with s being small, you can always find these loose charts in Legendre. So for small enough s, there's no instruction. You can always find these in any Legendre. So why is having large s good? Well, having large s is good because in that case, if you have a single one of these loose charts, then you could create more of these loose charts. Because what you can do is you can modify this picture. You kind of collapse it in the middle. Okay, this is maybe tricky to draw. So I'm taking my loose chart and I'm kind of pinching it in the middle so that it kind of goes down like this. Now, this also has some slope. But if this width is big enough, this slope will be small, and so you'll stay inside of this piece over here, because I remember I said this also had some bound on the slope. So basically you need this large width so that you can create more and more loose charts by pinching like this, and this slope will not be so big so that you stay inside of that chart. Okay.
Is this process going to terminate eventually? Like, do you lose slope every time you do it, or?
It's gonna get better every time, because like in this, like suppose, okay, let me just move over here. Okay, let me just draw the cross-section direction. So you have you're kind of going from this picture to like a picture like this, right? By pinching. In this region, the ratio of the height to the width is even better than it was before, and it can be made arbitrarily big. right? And now, in contact geometry, you're allowed to scale. So this one, this middle piece right here would actually be equivalent to some huge S if this is height 1. And so here you have many more loose charts than you had with. So basically this condition that S is greater than 1 allows you to have as many loose charts as you want. And that's actually a key point because otherwise, just finding one loose chart would not be enough, and you could never actually check whether something is loose in practice. Okay, so I guess let me say what a loose Legendre is. Definition. Legendre is loose if it has a loose chart. So, i.e., contact embedding. It's cube times this piece of the cotangent bundle cross the zigzag cross the zero section. Okay. Basically, a portion of your Legendrian looks like this loose chart. Okay.
Did you mean to write Rn minus 1 instead of Rn?
Okay, so now let me state the H principle, which is the Murphy. Says that if n is greater than or equal to 2, there is a full H principle for Legendrians with fixed loose charts. So what this means is you could consider, and let me call this loose charts. I'm just going to call this loose chart U. So let's consider Legendrians in Y with fixed loose chart U. You can also map this to formal Legendrians, which are actual Legendrians at this loose chart, and this is a weak homotopy equivalence. So let me contrast this with this statement over here. There's not an H principle for all Legendrians, partly due to this rigidity result using J-holomorphic curves, and partly, at least for the n equals 1 case, because of this formal class issue, and that's why this doesn't hold for n equals 1. When you start adding zigzags, well, actually, for the n equals 1 case, the proof is also going to fail, but as I'll explain in a second. But you saw the zigzags themselves are not in the same formal class as Legendre without the zigzag. Yeah.
It's known it's false if you don't have a fixed loose chart.
I don't know if anything has been written, but I think that's the expectation. But I think that's an interesting question. Like maybe how the loose chart moves. Remember something about the homotopy type of the manifold? Yeah, I don't know. Or maybe there's some like vibration sequence. Okay. Any more questions?
What is the analog of a loose chart or loose Legendre if you want an H principle for Lagrange?
Well, there's something called flexible Lagrangians, and they're Lagrangians, which are kind of built using handles that are attached along loose charts. They're built along handles that are attached along loose Lagrangians. So, okay, my next talk, I'm going to talk about Weinstein domains and flexible Weinstein domains. And there's going to be an analog that are called flexible Lagrangians. I'm not going to talk about that, but I think that's kind of the closest answer to your question that I know of. Okay, so now let me sketch the proof and end the talk there. It's a quite beautiful.
So for pi node, you can erase the loose chart condition, right?
Sorry, can you say that again?
Pi node, for just to classify two elements, you can forget all the loose. Right?
Oh, yeah. For pi node, you don't have to remember the loose charts because you can always bring the loose charts to where you can always make it fixed. Okay. Okay. So again, we first reduce to the graphical case, which is the case of where the ambient context structure is the one jet space. And let me just say that this uses an H principle for epsilon Lagrangians. So these are smooths of manifolds so that their tangent space is epsilon close to an isotropic subspace. So there actually is a full H principle for epsilon Lagrangians, but not actual Lagrangians. Okay. And so I'm not going to say anything else about this reduction. And now we're going to use the wrinkled embedding theorem. Run at least two, and I'm going to draw the picture for n equals 2 case. So you have this high mountain, you want to go up, but you want to keep your slope close to 0. And so you apply this wrinkled embedding H principle, and you get these wrinkles that I drew in the very beginning. So the cross section looks like a zigzag like this, and the slopes of these should be quite small, right? Remember that this is like a sharp cusp like this, and in two-dimensional case, this zigzag dies in 2 different ways. And well, now you'd like to just say, well, now you finished the problem because the slope is this is a Legendre, and the slope of this is close to this one. But the issue is that actually this does not lift to a smooth Legendre. So in the beginning, I said having cusps lifts to a smooth Legendre, but these wrinkles, they have these unfurled swallowtails, and these unfurled swallowtails, they do have Legendre lifts, but that Legendre lift in the one jet space is not smooth. Which is good because otherwise you would be proving a full H principle for Legendres, right? You would start with this and the deformant form these wrinkles. If that were smooth, well, then the full H principle would run through. So the issue is that the lift of this wrinkle is not quite a smooth Legendre.
Is the picture like I have a bit like a spiral, and then one of the circles becomes smaller and smaller and smaller, and I pinch it tight?
And maybe that's a good way to see it. I've actually never thought about it, but that seems reasonable. Yeah. Okay. So issue. These 2 points. Okay. But remember that we assumed that we had a loose chart to start with. So really, somewhere, let's say over here, we had this loose chart. That was one of our assumptions, right? We're only trying to prove the H principle for Legendrians that have a loose chart to start with, and then we formed these wrinkles. So really, we have this up here, and the only issues are at the equators of these spheres. So now the trick is to use this single loose chart to resolve these bad points where it doesn't lift as smooth. So let me try to draw the picture. And then over here, you had this loose chart. And loose charts will, that's the best way to draw this. Okay. So you had this loose chart, and it was kind of propagating throughout. And what you do is, notice that if you just erase these endpoints of this wrinkle, it just looks like a thickened loose chart, right? So what you can do is, you could pick an arc, at least in the n=1 case, that connects the loose chart. So I'm picking like an arc that goes here, and then an arc that comes back, and then for this one, an arc that goes from this endpoint to this endpoint. So these are wrinkles with markings that connect their equator to the loose charts. And these are just paths. And now the trick is, well, this looks like a zigzag cross an interval. This looks like a zigzag cross an interval. There's some bad regions here, but we can erase these and just connect it to the loose chart that we already had. So I'm connecting it like this, and this part kind of gets connected like this. This part gets connected like this. And now the whole thing just looks like cusps.
But you're no longer fixing a loose chart.
Okay, this is the non-parametric case. So again, the idea is you have these points where the lift is not smooth. You'd like to get rid of them. And the way to do that is to pick paths to the loose chart and erase these points. And along the path, just draw like a family of zigzags, which you can do locally. And now this whole thing will lift to a loose Legendre. All right, so that's the proof. And next time I'll give some applications of this. Okay, thank you.
Are there any questions for Oleg?